The colonization of Mars has become a topic of great interest, not only in scientific circles but also in popular culture, as humanity looks towards the stars with dreams of establishing a presence on another planet. The idea of humans living on Mars, with its red, rocky surface and thin atmosphere, raises numerous questions about how we would adapt to such an environment. Scientists and engineers are exploring various methods for making Mars hospitable, or at least survivable, for human beings. One significant challenge is the planet's atmosphere, which is composed of over 95% carbon dioxide and has only trace amounts of oxygen. This means that, before colonization can begin, we would need to develop technologies for producing breathable air, possibly through the extraction of oxygen from Martian regolith, or soil. Another critical aspect of Mars colonization is the availability of water, which is essential for human survival, agriculture, and other activities. Recent missions, including those conducted by NASA's Perseverance rover, have discovered signs of ancient riverbeds and polar ice caps, indicating that water ice exists on the planet. Scientists are now studying methods to extract this water, which could be used for drinking, growing food, and even producing fuel through electrolysis. The logistics of transporting people and supplies to Mars is another hurdle. Current plans involve using powerful rockets, like SpaceX's Starship, aimed at carrying large numbers of people and equipment on long-duration flights. This raises questions about the health risks involved, as the journey could take several months, exposing astronauts to higher levels of radiation and the psychological effects of isolation. Once on Mars, colonists would need to build habitats that can withstand extreme temperatures, which can swing from -100 degrees Celsius at night to +20 degrees during the day. Innovative concepts for habitats include using Martian soil to create bricks, or using inflatable structures that can be easily transported and set up. Growing food on Mars is also a significant concern, as traditional farming methods may not work in the thin atmosphere and lower gravity. Researchers are exploring hydroponics and aeroponics, which allow plants to grow without soil, using nutrient-rich water or mist instead. Communication with Earth presents another challenge. Due to the distance, signals can take between 3 and 20 minutes to travel one way, making real-time communication impossible. This could pose difficulties in coordinating efforts and providing support from Earth. Furthermore, the social dynamics of a Mars colony could be vastly different from those on Earth, with a small population living in close. In recent years, private companies have taken on an increasingly significant role in space exploration, shifting the landscape from a government-dominated field to one where commercial entities are vital players. This transition began in earnest in the early 2000s, with the establishment of companies like SpaceX, Blue Origin, and Virgin Galactic, each with its own unique approach to space travel and exploration. SpaceX, founded by Elon Musk, has made headlines with its ambitious goal of reducing the cost of space travel and enabling human colonization of Mars. Their Falcon 9 rocket has become a workhorse, regularly delivering cargo to the International Space Station, while the development of the Starship craft aims to facilitate deeper space missions. Meanwhile, Blue Origin, started by Jeff Bezos, focuses on reusable rocket technology and suborbital tourism, seeking to make space accessible to more people. Virgin Galactic, founded by Richard Branson, has taken a different route, concentrating on space tourism, offering brief experiences that allow civilians to experience weightlessness and see the curvature of the Earth. These companies are not only innovating technology, but also collaborating with government agencies like NASA, which has increasingly turned to the private sector for assistance. Under programs like Commercial Crew, NASA has contracted private companies to transport astronauts to and from the ISS, which has helped to spur competition and lower costs, while also allowing NASA to refocus its resources on deeper space exploration, such as missions to the Moon and Mars. Moreover, private companies are also venturing into satellite deployment, providing services that range from communications to Earth observation, which are crucial for modern society. and can generate revenue for these enterprises. The impact of private companies on space exploration goes beyond just technology and contracts. It also encompasses the vision of making space more accessible. With the push towards commercial space travel, the idea that ordinary people could one day experience space firsthand is becoming more feasible. As these companies continue to innovate, the potential for future developments seems boundless, with plans for lunar bases, asteroid mining, and even interplanetary travel becoming serious topics of discussion. The excitement surrounding these advancements has attracted significant investment, fostering a new era of entrepreneurship in the space sector, where startups are emerging to tackle various challenges, from sustainable space travel to the development of new propulsion systems. Furthermore, the role of private companies has raised important discussions about regulation and safety, as the rapid pace of development often outstrips existing frameworks. Governments are now tasked with ensuring that these companies operate safely while also encouraging innovation. Advances in propulsion technology are transforming the way we think about travel, not just here on Earth, but also in space. In recent years, researchers have been making significant strides in various forms of propulsion systems, which could change the future of transportation. One of the most exciting developments is the progress in electric propulsion systems, particularly ion thrusters, which have been used successfully in several space missions. Unlike traditional chemical rockets, which burn fuel to create thrust, ion thrusters work by using electricity to accelerate ions, producing a gentle but continuous thrust that can last for much longer periods, making them incredibly efficient for deep space missions. Another groundbreaking advancement is the development of plasma propulsion systems, which use superheated gas to create thrust. These systems have the potential to provide even greater efficiency and speed than ion thrusters, allowing spacecraft to travel farther and faster. For instance, NASA's Variable Specific Impulse Magnetoplasma rocket, or VASIMAR, is a cutting-edge plasma engine that could enable human missions to Mars in a fraction of the time it currently takes. This could fundamentally change our approach to interplanetary exploration, making it more feasible and less time-consuming. On Earth, advancements in electric and hybrid propulsion systems are reshaping the aviation industry. Companies are now developing electric planes, which promise to reduce emissions and lower operating costs. These aircraft use electric motors powered by batteries or hybrid systems, combining traditional engines with electric propulsion to improve fuel efficiency. The emergence of urban air mobility is another exciting area, where electric vertical takeoff and landing vehicles, or eVTOLs, are being designed to operate in urban environments, providing quick transportation options that could alleviate traffic congestion. Moreover, researchers are exploring the potential of nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant, creating a high-thrust option for future space missions. This technology could allow spacecraft to reach distant destinations in less time, opening up possibilities for human exploration of Mars and beyond. The promise of nuclear propulsion lies in its ability to deliver more thrust than conventional chemical systems, while also providing a more efficient use of fuel, which is crucial for long-duration space missions. The field of advanced propulsion is also seeing innovations in the realm of magnetohydrodynamics, or MHD, which involves using magnetic fields to control the flow of electrically conductive fluids, like plasma or liquid metals, to create thrust. This technology has the potential to revolutionize both terrestrial and space travel by providing highly efficient propulsion systems that could operate as humanity looks to the stars. The concept of space mining emerges as a promising venture, offering the potential to extract valuable resources from asteroids, moons, and other celestial bodies. However, this exciting prospect brings with it a myriad of ethical considerations that must be addressed. One major concern is the impact on the environment, both in space and on Earth. While extracting resources from asteroids might seem like an ideal solution to depleting terrestrial resources, the process itself could generate space debris, which poses a risk to satellites and other spacecraft. Additionally, the mining operations could disturb the natural state of celestial bodies, raising questions about the preservation of these environments for future scientific study, as well as the potential for alien life forms that we may not yet understand. Another critical ethical issue relates to ownership and governance. The Outer Space Treaty of 1967, signed by over 100 countries, including major spacefaring nations, states that no one can claim sovereignty over celestial bodies. This raises questions about who has the right to mine these resources. Would it be the country that sends the spacecraft? Or should it be a collaborative effort among nations? The lack of clear legal frameworks can lead to conflicts and competition, potentially creating a new frontier of territorial disputes in an already crowded space. Moreover, there are social implications to consider. The benefits of space mining, such as the extraction of precious metals or rare earth elements, could be substantial, but who would reap these benefits? If a few wealthy corporations or nations dominate space mining, it could exacerbate existing inequalities on Earth, as those who are already privileged gain even more resources and power, leaving behind developing nations that might struggle to access the technology and expertise needed to participate in this new industry. Then, there's the question of technological advancement and its ramifications. The technology required for space mining is still in its infancy, and while advancements could lead to amazing discoveries, they could also pose ethical dilemmas. For instance, if we develop technologies that can alter celestial bodies, what responsibilities do we have to ensure that we do not harm potential ecosystems or interfere with the cosmic environment? The prospect of terraforming other planets or moons for mining purposes also raises moral questions about our role in the universe. Should we play God, reshaping worlds to suit our needs? Or should we take a more conservationist approach, leaving these celestial bodies as they are? Furthermore, the psychological impact on humanity cannot be overlooked. As we venture further into space, when humans venture into space, they encounter a unique environment known as microgravity, which is often described as weightlessness. And this condition has profound effects on the human body. Microgravity occurs when an object is in free fall, creating a sensation of floating, as experienced by astronauts aboard the International Space Station, or ISS, where they orbit Earth at high speeds. In this environment, the body undergoes several adaptations, primarily due to the lack of gravitational pull. For instance, one of the most immediate changes is the loss of muscle mass. Without the need to support their own weight, astronauts can lose up to 20% of their muscle strength in the first few weeks of a mission. Additionally, bones also weaken, as the body reduces the production of bone tissue, leading to a condition similar to osteoporosis. This occurs because the mechanical stress that bones usually experience on Earth is significantly reduced in microgravity. Another interesting adaptation involves fluid distribution within the body. In a normal gravitational environment, fluids tend to pool in the lower parts of the body, but in microgravity, fluids shift towards the head, which can cause facial puffiness and increased intracranial pressure. This change can lead to visual impairments for some astronauts, as the pressure affects the optic nerves. Furthermore, the cardiovascular system also adapts, with the heart becoming more spherical in shape, as it no longer needs to pump blood against gravity. This can result in orthostatic intolerance, a condition where astronauts may feel faint or dizzy when returning to a gravity environment, as their bodies struggle to readjust. Moreover, microgravity affects the way the body processes nutrients and energy. Studies have shown that astronauts may experience changes in metabolism, leading to alterations in how the body burns fat and carbohydrates. These shifts can also influence immune system function, with some researchers suggesting that microgravity might impair immune responses, making astronauts more susceptible to infections while in space. The psychological effects of long-term microgravity are also noteworthy. Astronauts often report feelings of isolation and stress due to the confined environment and the absence of natural stimuli found on Earth. To combat these challenges, astronauts engage in regular exercise, utilizing specially designed equipment that simulates resistance training, which helps to mitigate muscle and bone loss. NASA has developed protocols to keep astronauts fit and healthy during their missions, including aerobic workouts and resistance exercises, which are crucial for maintaining physical health while living in space. Additionally, scientists are actively researching ways to better understand the long-term impacts of microgravity on. The search for extraterrestrial life is a captivating topic that has fascinated humanity for decades, if not centuries. Scientists and enthusiasts alike ponder the possibility of life beyond Earth, looking to the vastness of the universe for signs that we are not alone. The quest began with early astronomers who gazed at the night sky, imagining distant worlds and potential life forms. Fast forward to today, and we have advanced tremendously in our understanding of the cosmos, thanks to technology and exploration missions. One of the key methods of searching for extraterrestrial life involves studying extreme environments on Earth, where life thrives in conditions once thought to be uninhabitable, such as deep-sea vents, acidic lakes, and the frozen landscapes of Antarctica. These discoveries suggest that life could exist in similarly extreme conditions on other planets or moons, such as Europa, a moon of Jupiter, which is believed to have a subsurface ocean beneath its icy crust, or Enceladus, a moon of Saturn, known for its geysers that shoot out water vapor and organic compounds. Moreover, the study of exoplanets, planets that orbit stars outside our solar system, has revolutionized the search for alien life. Astronomers have identified thousands of these worlds, some of which lie in the so-called Goldilocks zone, where conditions might be just right for liquid water, a crucial ingredient for life as we know it. The Kepler Space Telescope, for example, has played a significant role in this discovery, allowing scientists to analyze the atmospheres of certain exoplanets for potential biosignatures, which are chemical indicators of life. In addition to these methods, researchers are also employing the technique of SETI, the search for extraterrestrial intelligence, which involves listening for signals from intelligent civilizations. By analyzing radio waves and other forms of communication from space, scientists hope to catch a glimpse of messages sent by advanced beings. Some of the most famous attempts to reach out to other civilizations include the Arecibo message sent in 1974, which contained information about humanity, our solar system, and the structure of DNA. The fascination with the possibility of alien life has also sparked numerous theories and speculations, ranging from the existence of microbial life on Mars, where rovers like Perseverance are actively seeking signs of ancient life, to the more controversial ideas of ancient astronauts and UFO sightings. While many claims about extraterrestrial encounters are often met with skepticism, the scientific community remains open-minded, continually searching. Space debris management strategies are becoming increasingly important as the number of satellites and other objects in orbit continues to rise. Space debris, which includes defunct satellites, spent rocket stages, and fragments from collisions, poses a significant threat to operational spacecraft and the International Space Station. One of the most common strategies for managing space debris is the use of active debris removal, which involves capturing and deorbiting larger pieces of debris. Several methods have been proposed for this purpose, including using robotic arms, nets, or harpoons to grab debris and then guiding it into a lower orbit where it will eventually burn up in the Earth's atmosphere. Another approach is the use of lasers to nudge debris out of its orbit, either by altering its trajectory or by increasing its drag, which helps it re-enter the atmosphere sooner. Additionally, there's a focus on improving satellite design to minimize the creation of space debris in the first place. This involves creating satellites that can deorbit themselves at the end of their operational lives, either by using built-in propulsion systems or by designing them to be more lightweight, which reduces the risk of fragmentation. The concept of passivation is also important, where satellites are designed to safely dispose of their remaining fuel and batteries before they are decommissioned, further reducing the risk of explosions or collisions in space. International collaboration plays a crucial role in debris management, with organizations like the United Nations Office for Outer Space Affairs and the European Space Agency leading efforts to establish guidelines and best practices for space debris mitigation. This includes tracking and cataloging space debris, which is essential for avoiding collisions and ensuring the safety of space missions. Some countries are developing advanced radar and telescope systems to monitor the positions of debris, allowing satellite operators to make adjustments to their orbits as needed. On a more innovative front, researchers are exploring the use of space tugs, which are small spacecraft designed to rendezvous with larger debris and either deorbit it or move it to a safer orbit. These tugs can be operated from Earth or autonomously, and they represent a forward-thinking approach to tackling the growing problem of space junk. Finally, public awareness and policy advocacy are vital components of debris management. As space becomes more accessible, it is essential to educate companies and governments about the importance of responsible practices in space exploration and satellite deployment. By fostering a culture of sustainability in space, we can work together to ensure that our orbital environment remains safe and usable for future generations. International collaboration in space missions has become increasingly important over the past few decades, as countries recognize that working together can lead to more significant achievements than going solo. For instance, the International Space Station, or ISS, is a prime example of this cooperation. This massive laboratory orbits Earth, and it involves the participation of 5 space agencies: NASA from the United States, Roscosmos from Russia, ESA from Europe, JAXA from Japan, and CSA from Canada. Each agency contributes its unique expertise, technology, and resources, allowing for a wide range of scientific experiments to be conducted in microgravity, which can lead to breakthroughs in various fields, including medicine, materials science, and environmental studies. Furthermore, international collaboration extends beyond just the ISS. In recent years, countries have come together for missions to Mars, with initiatives like the Mars Sample Return mission, which involves NASA and ESA working hand in hand to bring Martian soil back to Earth for analysis. This not only demonstrates the scientific potential of teamwork, but also showcases how countries can pool their knowledge and technology to tackle some of the most challenging objectives in space exploration. Moreover, international partnerships are also crucial in the development of new space telescopes. For example, the James Webb Space Telescope, which is set to revolutionize our understanding of the universe, is a collaborative effort involving NASA, ESA, and the Canadian Space Agency. The combined resources and expertise of these agencies have made it possible to create such a sophisticated instrument that promises to unveil new cosmic phenomena and provide insights into the formation of stars and galaxies. On a different note, the global nature of space exploration has also led to significant diplomatic relationships among nations. Space is often seen as a realm where countries can work together, setting aside geopolitical tensions to focus on shared human goals. This is evident in initiatives like the Artemis Accords, which aim to create a framework for international cooperation in lunar exploration and beyond. These accords encourage countries to participate in missions to the Moon, Mars, and other celestial bodies, emphasizing responsible exploration, transparency, and peaceful use of outer space. In addition to these large missions, smaller collaborative projects also play a vital role in fostering international ties. Universities and research institutions across the globe frequently engage in joint projects that utilize satellite data for climate monitoring, disaster response, and agricultural planning. By sharing data and resources, scientists can address challenges that transcend national borders, such as climate change, which affects everyone regardless of where they live. Finally, as we move towards space tourism, once a dream confined to the pages of science fiction, is rapidly becoming a reality. And this is not just about wealthy adventurers taking joyrides, but about opening up space exploration to a broader audience. Various companies, such as SpaceX, Blue Origin, and Virgin Galactic, are leading the charge, each with its unique approach to making space travel accessible. SpaceX has ambitious plans, aiming to take civilians on missions around the Moon, while Blue Origin focuses on suborbital flights that allow passengers to experience a few minutes of weightlessness, giving them a taste of what it's like to be in space. And Virgin Galactic has developed a spaceplane that can carry passengers to the edge of space. As technology advances, the costs associated with space travel are expected to decrease, making it more affordable for a larger segment of the population, potentially allowing people from different backgrounds to experience the wonders of the cosmos. The future of space tourism also raises questions about sustainability and the environmental impact of launching rockets, as the industry must consider how to minimize its carbon footprint while expanding access to space. Additionally, space tourism could lead to the development of new industries, from space hotels, where visitors could stay in orbit, to lunar resorts that offer breathtaking views of Earth from the Moon, and even transportation services for those wanting to explore the solar system. Moreover, as more private companies enter the space tourism market, competition is likely to drive innovation, leading to safer, faster, and more efficient travel options. This could also encourage collaboration between governments and private enterprises, fostering a new era of space exploration where public and private sectors work hand in hand. However, as exciting as space tourism may be, it also poses challenges, particularly concerning safety, as space travel involves risks that must be meticulously managed, and the industry will need to establish regulations to ensure passenger safety and protect the environment. Furthermore, the questions of who gets to go to space and how to make this experience equitable linger in the background, as it is crucial to ensure that the benefits of space tourism are shared widely, not just reserved for the elite. As we look to the future, it's evident that space tourism has the potential to change our relationship with space, allowing more people to experience its beauty and mystery, while also inspiring new generations to dream about what lies beyond our planet. Artificial intelligence, or AI, is making significant strides in space operations, transforming how we explore and understand the universe. One of the most fascinating applications of AI in this field is its use in autonomous spacecraft navigation. Traditionally, spacecraft relied heavily on ground control for guidance, but with advancements in AI, they can now analyze data in real time, make decisions, and adjust their trajectories without waiting for instructions from Earth. This not only speeds up the response time, but also allows for more complex and daring missions, especially in areas far from our planet, where communication delays can be substantial. Moreover, AI is being utilized to enhance the efficiency of satellite operations. Satellites collect vast amounts of data, from monitoring climate change to providing communication services. AI algorithms can process and analyze this data much faster than humans, identifying patterns and anomalies that might go unnoticed. For instance, in Earth observation, AI can help detect changes in land use, track wildlife populations, and even predict natural disasters, which can be crucial for timely interventions. In addition to navigation and data analysis, AI contributes to spacecraft health monitoring. Spacecraft systems are complex and require constant oversight to ensure they are functioning properly. AI systems can continuously monitor these systems, using machine learning to predict potential failures before they happen, which can save both time and resources during long-duration missions. This predictive maintenance can be especially beneficial for missions to Mars or other distant destinations, where repairs are not feasible. Furthermore, AI plays a crucial role in space exploration robotics. Robots equipped with AI can perform tasks such as sample collection, planetary surface analysis, and even construction of habitats on other planets. These AI-driven robots can operate in environments that are hazardous to humans, making them invaluable for missions that require exploration of extreme conditions, such as the surface of Mars or the icy moons of Jupiter. Interestingly, the use of AI in space operations is not solely about efficiency and safety. It also opens up new possibilities for scientific discovery. AI can help scientists sift through enormous datasets generated by telescopes and space missions, identifying celestial objects, categorizing them, and even discovering new phenomena. For example, AI has been instrumental in the search for exoplanets, utilizing data from space telescopes to identify potential candidates for further study. Another exciting aspect of AI in space is its potential for enhancing communication between Earth and spacecraft. AI systems can optimize communication protocols, ensuring that data transmission is efficient and reliable. This is particularly important for deep space missions, where bandwidth is limited, and every bit of terraforming planets, the idea of transforming a hostile environment into one suitable for human habitation, is a captivating concept that has captured the imagination of scientists, writers, and dreamers alike. When we think about the possibilities, Mars often comes to mind, as it is one of the most Earth-like planets in our solar system, possessing polar ice caps, seasons, and a day length similar to ours. The challenges, however, are monumental, beginning with the thin atmosphere, which is mostly carbon dioxide, and the harsh conditions that include extreme temperatures, radiation levels, and dust storms, making it difficult for any life to thrive. To terraform Mars, one proposed method is to release greenhouse gases into the atmosphere, which could trap heat and raise the temperature, potentially melting the ice caps to release water vapor. This idea, however, presents numerous scientific and ethical questions, such as the extent of human intervention in natural processes and the potential consequences on any existing Martian ecosystems, if they exist. Then there's Venus, often dubbed Earth's sister planet, which presents its own unique set of challenges for terraforming. With surface temperatures hot enough to melt lead, an atmosphere rich in carbon dioxide and sulfuric acid clouds, the concept of altering Venus into a more hospitable environment seems like a far-off dream. Some scientists propose creating floating cities in the upper atmosphere, where conditions are more temperate, but this idea raises questions about the feasibility of such structures and the long-term sustainability of life in such a harsh environment. The sheer scale of Venus presents a daunting challenge, as any terraforming effort would require unprecedented technology and resources, pushing the boundaries of our current engineering capabilities. Moreover, the moons of gas giants like Europa and Titan also ignite interest in terraforming possibilities. Europa, with its subsurface ocean beneath a thick layer of ice, holds the potential for life, and some scientists speculate about the possibility of creating a more accessible environment on its surface. On the other hand, Titan, Saturn's largest moon, has lakes of liquid methane and a dense atmosphere, which some believe could be transformed into a more Earth-like environment through the introduction of heat and oxygen. However, the technological and logistical hurdles of reaching these distant worlds, let alone altering them, are significant, and many experts agree that current space exploration capabilities must advance dramatically before terraforming becomes a feasible endeavor. In terms of the ethical implications of terraforming, there's an ongoing debate about the morality of altering other planets, especially if space exploration, often thought of as a distant pursuit, has significant implications for understanding and addressing climate change here on Earth. Through satellites, which orbit our planet, scientists gather vital data about the atmosphere, weather patterns, and even ocean temperatures, providing a clearer picture of how our climate is changing. These satellites, equipped with advanced sensors, monitor greenhouse gas emissions, track deforestation, and assess changes in land use, all of which are critical for climate research. For instance, NASA's atmospheric infrared sounder, aboard the Aura satellite, collects data on carbon dioxide levels, helping researchers understand how these gases are distributed in the atmosphere. Moreover, space exploration has enabled the study of Earth's climate over long periods. Historical data, collected from various missions, help scientists create climate models that predict future changes. This long-term perspective is essential because climate change is not just a fleeting issue, but a gradual process that unfolds over decades. For example, The European Space Agency's Climate Change Initiative aims to provide long-term, high-quality climate data records, which are crucial for understanding trends and making informed decisions about policy and conservation efforts. In addition to monitoring Earth's climate, space exploration can also offer innovative solutions to combat climate change. Technologies developed for space missions often find applications on Earth. For instance, the advancements in materials and energy efficiency from space technology can help create better solar panels, which in turn can increase the use of renewable energy. Furthermore, the research done on the International Space Station has led to breakthroughs in sustainable agriculture practices, which could potentially reduce the carbon footprint of food production. Another fascinating aspect of space exploration's impact on climate change is the study of other planets. By understanding the climate systems of Mars, Venus, and other celestial bodies, scientists gain insights into the effects of different atmospheric conditions and the processes that can lead to climate change. For example, studying the thick atmosphere of Venus, which is primarily composed of carbon dioxide, helps researchers understand the potential consequences of unchecked greenhouse gas emissions. Space exploration also fosters international collaboration, which is crucial in the fight against climate change. Space agencies, scientists, and researchers from different countries work together, sharing data and strategies to tackle this global issue. Joint missions, like those conducted by NASA and the Indian Space Research Organization, exemplify how collaborative space efforts can lead to more comprehensive climate data and innovative solutions. Public interest in space exploration can also drive awareness about climate change. As people become more fascinated with the cosmos, they often develop a greater appreciation. Robotics has become an essential part of space missions, transforming how we explore the universe. The advancement of robotic technology allows us to send machines into environments that are hostile to humans, such as the surface of Mars or the icy moons of Jupiter and Saturn. One of the most notable examples is the Mars rovers, like Curiosity and Perseverance, which are equipped with sophisticated tools to analyze soil samples, take high-resolution images, and even search for signs of past life. These rovers can operate autonomously, making decisions based on their programming, which enables them to navigate the challenging terrain of Mars without real-time human control. Moreover, robotics play a crucial role in satellite deployment and maintenance. Satellites are vital for communication, weather forecasting, and Earth observation, and they often require repairs or upgrades. Robotics, such as the Dextra robot used on the International Space Station, can perform delicate tasks in space, reducing the need for astronauts to undertake dangerous spacewalks. This robot can change out parts, perform inspections, and handle tools that would be cumbersome for humans in a zero-gravity environment. In addition to repairs, robotic spacecraft have been pivotal in deep space exploration. The Voyager probes, launched in the 1970s, are equipped with instruments that have provided invaluable data about the outer planets and beyond. These robots send back information about the atmosphere, magnetic fields, and even the presence of rings around planets, allowing scientists to gather knowledge that would be impossible to obtain otherwise. Another fascinating application of robotics in space is the concept of using autonomous drones on other celestial bodies. NASA has been testing drones on Mars, which can cover more ground than rovers by flying over obstacles that would slow down wheeled vehicles. This technology could revolutionize how we explore planetary surfaces, giving us a bird's-eye view and the ability to survey areas that are otherwise inaccessible. Robots are also crucial for future missions to asteroids and comets, where they can gather samples and analyze materials that could provide insight into the early solar system. The OSIRIS-REx mission, for example, successfully collected samples from the asteroid Bennu, showcasing the ability of robotic systems to perform complex maneuvers and sample collection in deep space. In addition to exploration, robotics is being considered for potential colonization efforts. Concepts for lunar bases or Martian habitats include robotic systems that could prepare the environment for human arrival, constructing shelters, and producing essential resources like water and oxygen. Lunar bases have emerged as a fascinating topic within space exploration, drawing attention from scientists, engineers, and space enthusiasts alike. The feasibility of establishing permanent habitats on the moon is not just a distant dream, it is becoming increasingly realistic, thanks to advancements in technology and our understanding of lunar resources. The moon, with its relatively close proximity to Earth, offers a unique opportunity for research, scientific discovery, and even potential commercial ventures. One of the key factors making lunar bases feasible is the presence of resources such as water ice, which has been discovered in permanently shadowed craters. This water can be used for drinking, growing food, and even converted into hydrogen and oxygen for rocket fuel, significantly reducing the need to transport all supplies from Earth, which is both costly and time-consuming. Moreover, the moon's lower gravity, compared to Earth, allows for easier launching of spacecraft. This could lead to a thriving space economy, where lunar bases act as launch points for deeper space exploration, including missions to Mars and beyond. The benefits of having a lunar base extend into scientific research as well. Scientists can conduct experiments in a low-gravity environment, and the moon serves as an excellent location for astronomical observatories, free from Earth's atmospheric interference. Additionally, establishing a base on the moon could serve as a stepping stone for international collaboration in space exploration, fostering partnerships among countries and encouraging shared knowledge and resources. The technological challenges of building and maintaining a lunar base are significant, including life support systems, radiation protection, and the creation of sustainable habitats. However, innovations in robotics, 3D printing, and habitat design are paving the way for solutions to these challenges. The idea of using lunar regolith, or the moon's surface material, for construction purposes is particularly promising, as it would allow for building structures without relying heavily on materials brought from Earth. Furthermore, the establishment of a lunar base could lead to new educational opportunities, inspiring the next generation of scientists and engineers, and reigniting public interest in space exploration, which has been waning since the Apollo missions. Additionally, lunar bases could play a crucial role in understanding how living organisms adapt to space environments, providing essential insights for future long-duration missions. The psychological aspects of living on the moon, such as isolation and confinement, are other areas ripe for research, helping to prepare for human missions to Mars, which will require longer periods away from Earth. In summary, while there are many hurdles to overcome, the feasibility and potential benefits of establishing long-duration space travel presents unique psychological challenges that can significantly impact astronauts as they venture far from Earth for extended periods, isolated in confined environments, and cut off from familiar social structures. Research has shown that the absence of natural light, the constant hum of machinery, and the limited personal space aboard spacecraft can lead to feelings of anxiety, depression, and loneliness. In a space station or a spacecraft, crew members often experience a phenomenon known as group dynamics, where interpersonal relationships can become strained due to the high-stress environment and the close quarters in which they live. Conflicts, misunderstandings, and emotional stress can arise more easily, leading to potential breakdowns in communication, which can complicate teamwork, a critical element for mission success. Moreover, the concept of time can significantly alter an astronaut's psychological state. In space, the usual markers of time, such as the rising and setting of the sun, are absent, which can disrupt circadian rhythms and lead to sleep disturbances. Poor sleep quality further exacerbates feelings of irritability and fatigue, making it even more challenging for astronauts to cope with the demands of their missions. Studies have indicated that maintaining a regular sleep schedule and incorporating light therapy can help mitigate these effects, but it requires conscious effort and discipline. Isolation and confinement are also critical factors to consider. As astronauts remain in space for months, they may feel disconnected from their loved ones, leading to homesickness and a longing for Earth. This emotional strain can be exacerbated during long missions, such as trips to Mars, where communication delays mean that astronauts cannot receive immediate responses from family and friends. To combat these feelings, space agencies often encourage astronauts to maintain a routine that includes leisure activities, exercise, and regular communication with support teams on Earth, which can help maintain morale and provide a sense of normalcy. Furthermore, the psychological preparation for long-duration missions is as crucial as physical training. Astronauts undergo rigorous psychological evaluations and training to equip them with coping strategies for managing stress and emotional challenges. They learn techniques for conflict resolution, mindfulness, and maintaining a positive mindset, which are essential skills during the mission. The use of virtual reality VR and simulation technologies is also being explored, allowing astronauts to practice dealing with potential stressors before they encounter them in space. Finally, the study of the psychological effects of long-duration space travel extends beyond the individual astronauts. It offers valuable insights into human behavior and resilience, which can inform not just future space missions, but also how space law and governance is a fascinating and complex field that has evolved significantly since humanity first ventured beyond our planet. As nations and private companies increasingly explore, utilize, and even settle in outer space, the need for a clear legal framework has become more pressing than ever. The foundation of space law is largely built on international treaties, with the most important being the Outer Space Treaty, which was adopted in 1967. This treaty establishes that outer space is the province of all humankind, meaning that no single nation can claim sovereignty over any celestial body, such as the Moon or Mars. It also emphasizes that space exploration should be conducted for the benefit of all countries, not just those with advanced space programs. Another key aspect of space law is the principle of non-appropriation, which states that no one can own a part of outer space, or any celestial body. This rule aims to prevent any conflict over territory in space, as well as to ensure that all nations can access and benefit from the resources available in outer space. Additionally, the Outer Space Treaty outlines that activities in space must be conducted in a manner that avoids harmful contamination of space environments, which has become an increasingly important consideration as more missions are launched. In the years following the Outer Space Treaty, several other agreements were established to address specific issues related to space activities. For example, the Rescue Agreement of 1968 obliges countries to assist astronauts in distress, while the Liability Convention of 1972 holds states responsible for damages caused by their space objects. The Registration Convention, also from 1976, requires countries to provide information about their space objects to the United Nations, promoting transparency in space operations. As private companies like SpaceX, Blue Origin, and others enter the field, there is an ongoing debate about how existing laws apply to commercial activities in space. This has led to discussions about the need for updated regulations that can accommodate the rapidly changing landscape of space exploration and exploitation. For instance, the commercialization of resources, such as mining asteroids for precious metals, raises important legal questions about ownership and profit sharing, as current treaties do not explicitly address these issues. Moreover, the rise of space tourism, with companies planning to take civilians into space, adds another layer of complexity to space governance. Questions about safety, liability, and the rights of space tourists are emerging as crucial points of discussion. As nations and companies prepare for potential human settlements on the Moon or Mars, the governance of these new territories is. Science fiction has played a significant role in shaping our dreams and aspirations for space exploration, capturing the imaginations of generations and inspiring real-world advancements in technology and science. From the early works of Jules Verne, whose novel From the Earth to the Moon imagined a journey to the moon long before it was scientifically feasible, to the more intricate and thought-provoking narratives of writers like Arthur C. Clarke and Isaac Asimov, science fiction has provided a canvas where the possibilities of space travel are painted with both creativity and speculation. Clarke's concept of satellites, especially the geostationary satellite, was not just a flight of fancy. It laid the groundwork for modern communication technologies that we rely on today, demonstrating how speculative ideas can translate into practical applications. Moreover, science fiction has often anticipated technological advancements, pushing the boundaries of what is possible. The iconic series, Star Trek, introduced concepts like warp drive and transporters, which, while still in the realm of fiction, have inspired scientists and engineers to explore new theories in physics and engineering. The show's optimistic view of the future, where humanity explores the cosmos alongside other intelligent species, has encouraged a culture of collaboration and curiosity in scientific communities, leading to initiatives like NASA's Artemis program, which aims to return humans to the moon and eventually send crewed missions to Mars. The visual medium of film and television has also contributed immensely to public interest in space exploration. Movies like Interstellar and The Martian have not only entertained audiences, but have also sparked discussions about black holes, time dilation, and the challenges of living on another planet. They bring complex scientific concepts to a broader audience, making them more accessible and engaging, while also highlighting the importance of scientific accuracy, as seen in the collaboration between filmmakers and scientists to create realistic portrayals of space phenomena. Furthermore, the influence of science fiction extends beyond just inspiration. It has also fostered a sense of urgency regarding space exploration. Works like Kim Stanley Robinson's Mars trilogy explore the challenges of colonizing Mars, delving into ecological and societal issues that could arise, prompting readers and policymakers to think critically about our future in space. This genre has opened up dialogues about sustainability and the ethical implications of space colonization, urging humanity to consider not only the technological aspects, but also the moral responsibilities that come with exploring new worlds. In addition, the rise of social media and online communities has allowed science fiction fans to engage with one another, sharing ideas and dreams of space exploration. Astrobiology, a fascinating field that combines aspects of biology, chemistry, and astronomy, seeks to understand the potential for life beyond Earth. Scientists involved in astrobiology explore the conditions necessary for life, as well as the environments of celestial bodies, to determine where life might exist, or where it once might have existed. One of the most thrilling aspects of astrobiology is the search for habitable exoplanets, planets that orbit stars outside our solar system and have conditions that could support life as we know it. Around the world, astronomers use powerful telescopes and advanced technology, such as the Kepler Space Telescope and the Transiting Exoplanet Survey satellite, to discover these distant worlds. To qualify as habitable, an exoplanet typically needs to be located in the Goldilocks zone, which is the region around a star where temperatures are just right, not too hot and not too cold for liquid water to exist. Water is considered a key ingredient for life, making the search for planets with the potential for liquid water crucial. Recent discoveries, like those of the TRAPPIST-1 system, which contains several Earth-sized planets in its habitable zone, have sparked excitement among scientists and the general public alike. These planets may have conditions that allow for the presence of liquid water and potentially life. However, finding a habitable exoplanet is just the beginning. Scientists also study the atmosphere of these planets to assess their habitability. The presence of certain gases, like oxygen and methane, can indicate biological activity. By using spectrometry techniques, researchers can analyze the light that passes through a planet's atmosphere when it transits in front of its star. This method allows scientists to identify the chemical composition of the atmosphere and search for signs of life. Another intriguing aspect of astrobiology is the study of extremophiles, organisms that thrive in extreme environments on Earth. such as deep-sea hydrothermal vents or highly acidic lakes. By understanding how these organisms survive in harsh conditions, scientists can better predict what forms life might take on other planets, where conditions might be very different from those on Earth. This knowledge broadens the scope of where we might find life, extending our search to moons in our solar system, like Europa and Enceladus, which have subsurface oceans beneath their icy surfaces. Additionally, the search for intelligent extraterrestrial life poses another layer of complexity. Programs like SETI, or the search for extra Earth observation satellites, play a crucial role in monitoring our planet, providing invaluable data that helps us understand environmental changes, track weather patterns, and manage natural resources effectively. These satellites are equipped with advanced sensors and imaging technology, allowing them to gather information about the Earth's surface, atmosphere, and oceans. One of the primary benefits of these satellites is their ability to monitor climate change, offering detailed insights into temperature variations, ice melting in polar regions, and deforestation trends. By collecting data over time, scientists can analyze patterns that might indicate long-term changes in the Earth's climate, which is essential for making informed decisions about climate policy and conservation efforts. Moreover, Earth observation satellites enhance disaster management, providing real-time data during natural disasters such as hurricanes, floods, and wildfires. For instance, satellite imagery can help predict the path of a hurricane, allowing emergency services to prepare and respond more effectively, potentially saving lives and minimizing damage. Additionally, these satellites assist in assessing the impact of disasters after they occur, helping governments and organizations allocate resources for recovery and rebuilding efforts. Agriculture also benefits significantly from Earth observation satellites, which enable farmers to monitor crop health and soil conditions. By using satellite data, farmers can make better decisions about irrigation, fertilization, and pest management, ultimately leading to increased yields and more sustainable practices. This technology is particularly valuable in regions where traditional methods of monitoring crops might be limited due to geography or lack of infrastructure. Furthermore, the satellites contribute to urban planning and development by providing city planners with critical information about land use and urban sprawl. They can analyze growth patterns, traffic congestion, and pollution levels, allowing for more effective management of urban environments. This data helps in creating sustainable cities that can accommodate growing populations while minimizing environmental impact. In addition to these practical applications, Earth observation satellites also play a key role in scientific research. They help researchers study phenomena such as ocean currents, atmospheric changes, and the health of ecosystems, contributing to our understanding of complex systems and their interconnections. This research is crucial for advancing our knowledge in fields like meteorology, oceanography, and environmental science. As technology continues to evolve, the capabilities of Earth observation satellites will only improve. The development of small satellites, or CubeSats, has made it possible for more organizations, including universities and startups, to participate in Earth observation efforts. These smaller, more affordable satellites can be launched in groups, allowing for more frequent and detailed monitoring of the Earth. This democratization of satellite technology opens up space-based solar power. Is an intriguing concept that has gained attention in recent years, as it holds the promise of capturing solar energy from space and transmitting it back to Earth. The basic idea is to place solar panels in orbit around the Earth, where they can collect sunlight without the interruptions caused by the atmosphere, clouds, or the day-night cycle. This means that solar panels in space can potentially generate energy continuously, providing a steady and reliable source of power. The technology behind space-based solar power involves several components, including satellites equipped with solar panels, energy conversion systems, and wireless power transmission methods, such as microwave or laser beams. One of the main opportunities presented by space-based solar power is its ability to provide clean energy to remote or disaster-stricken areas, where traditional power infrastructure may be damaged or non-existent. Imagine a world where energy could be beamed down from space to provide electricity to places that need it most, such as during natural disasters or in regions lacking reliable power sources. Additionally, this approach could significantly reduce our reliance on fossil fuels, contributing to global efforts to combat climate change and promote sustainability. However, there are also several challenges that need to be addressed before space-based solar power can become a reality. One significant hurdle is the high cost of launching and maintaining satellites in orbit. The technology required to build and deploy these systems is still in its infancy, and the initial investment can be substantial. Furthermore, the efficiency of converting solar energy into a form that can be transmitted back to Earth is still being researched, meaning improvements are necessary to make this technology viable. Another challenge is the potential impact on the environment and space debris. As more satellites are launched, the risk of collisions in space increases, which could create debris that poses a threat to other spacecraft. Additionally, there are concerns regarding the safety of transmitting energy back to Earth, particularly regarding the effects of concentrated microwave or laser beams on wildlife and human health. Moreover, regulatory and international cooperation will be essential for the successful implementation of space-based solar power. Since space is a global commons, collaboration among nations will be crucial to address legal and ethical considerations related to ownership, usage, and potential geopolitical tensions that may arise from harnessing energy from space. In summary, while space-based solar power presents a unique and promising opportunity for providing renewable energy, it also faces significant challenges that need to be overcome. Ongoing research, technological advancements, and international collaboration will be key factors in determining whether this innovative idea can be. The International Space Station, often referred to as the ISS, has been a remarkable symbol of international collaboration in space exploration. But what does the future hold for this incredible facility? As we look ahead, several factors come into play. First, the ISS has been continuously inhabited since November of 2000, serving as a laboratory for scientific research, technology development, and international cooperation. The current agreements between the space agencies of the United States, Russia, Europe, Japan, and Canada extend the station's operational life until at least 2024, but there are discussions to continue its use even longer, possibly until 2028 or beyond, depending on funding and the condition of the station. One of the critical considerations for the future of the ISS is its aging infrastructure. Over the years, the station has faced wear and tear, and with components that are decades old, the need for upgrades and maintenance is essential. NASA, along with its international partners, is working on various plans to ensure that the ISS remains safe and functional for its crew, which includes astronauts conducting experiments in microgravity, such as studying the effects of space on the human body, and testing new technologies for future missions to the Moon and Mars. As commercial interest in space grows, we are also witnessing a shift in how the ISS operates. Private companies are becoming more involved, with plans to conduct commercial research, manufacturing, and even space tourism aboard the ISS. This means that the station could serve as a hub for innovation, where private enterprises can develop technologies and products that benefit life on Earth, while also paving the way for future deep space exploration. Moreover, the future of the ISS is intertwined with the development of new space stations. NASA has announced its intention to transition to a new phase of low Earth orbit operations, which may include partnerships with commercial entities to build new space stations that could succeed the ISS. These new platforms might offer more specialized facilities for research, manufacturing, and even entertainment, expanding the possibilities of what can be achieved in space. In addition to these developments, the role of international cooperation remains vital. The ISS has demonstrated how countries can work together towards common goals, and this collaborative spirit is likely to continue in future projects. The lessons learned from operating the ISS will inform new missions to the Moon, Mars, and beyond, where the need for teamwork and shared resources will be crucial. As we contemplate the future of the International Space Station, it is clear that its legacy will not only be measured by When we think about space exploration, the vastness of the cosmos often overshadows the unique challenges faced by astronauts, particularly when it comes to their health. As humans venture into space, the effects of microgravity and radiation on the body become significant concerns, prompting medical innovations specifically designed for astronauts. One area of focus is the development of advanced wearable health monitoring devices, which can track vital signs, such as heart rate, oxygen levels, and even stress indicators in real time. These devices, equipped with sensors and algorithms, help doctors on Earth monitor astronauts' health during long missions, ensuring any potential health issues are addressed promptly. Additionally, researchers are exploring telemedicine, which allows astronauts to consult with medical professionals on Earth through video calls, ensuring they receive expert advice even when they are hundreds of miles away from immediate medical help. This technology is crucial, especially for long-duration missions to Mars or other distant destinations. Another important aspect of space health is the study of bone density loss and muscle atrophy caused by prolonged exposure to microgravity. To combat this, innovative exercise regimens have been developed, incorporating resistance training and cardiovascular workouts tailored to maintain astronauts' physical health while in orbit. Moreover, nutrition plays a vital role in maintaining health in space, leading to the creation of specialized space food that ensures astronauts receive balanced meals, rich in essential nutrients, without compromising on taste or texture. Research is ongoing into how certain foods, such as fruits and vegetables, can be grown in space to provide fresh produce for astronauts, not only enhancing their diet, but also improving their mental well-being. Another fascinating development is in the field of mental health, as isolation and confinement can take a toll on astronauts' psychological well-being. Programs have been implemented to provide mental health support, including virtual reality experiences, which can help astronauts relax and escape the stresses of their environment. This innovative approach allows for a temporary reprieve from the confined space of a spacecraft, offering a glimpse of nature or other calming visuals. As we delve deeper into the realms of space health, researchers are also investigating the potential use of 3D printing technology to create medical supplies and even organs in space, should the need arise. This groundbreaking innovation could revolutionize how medical emergencies are handled during missions, providing immediate access to necessary tools and materials. Furthermore, ongoing studies are focused on understanding how space travel affects the human microbiome, as changes in gut bacteria can influence overall health, immunity, and even mood. In summary, as humanity looks beyond our planet, the potential of 3D printing in space emerges as a game-changer for future exploration and colonization. This innovative technology, which has already transformed manufacturing on Earth, could play a crucial role in building habitats, creating tools, and even producing food in the harsh environment of space, where resources are scarce. Imagine astronauts on a mission to Mars, able to print replacement parts for their equipment, rather than relying on the long and expensive process of sending supplies from Earth. This capability could significantly reduce the need for resupply missions, making deep space exploration more feasible and cost-effective. NASA has been actively researching the use of 3D printing in space, recognizing its potential to create structures and components using materials that are available on other celestial bodies, such as lunar regolith or Martian soil. By utilizing in-situ resources, astronauts could manufacture everything from spare parts to entire habitats, tailored specifically to their needs and designed for the unique challenges of the space environment. This approach not only saves on transport costs, but also minimizes the environmental impact of launching materials from Earth. Moreover, 3D printing can facilitate the creation of complex geometries that traditional manufacturing methods may struggle to achieve. This is particularly important in space, where weight and space are at a premium. For instance, intricate designs for tools or parts can be printed on demand, allowing for greater customization and efficiency. Additionally, research is ongoing into 3D food printing, which could provide astronauts with nutritious meals made from ingredients that are shelf-stable and easy to transport, ensuring they receive the necessary sustenance during long missions. Furthermore, the technology may help bridge the gap for future colonization efforts, as it allows for the construction of habitats that can withstand the extreme conditions of other planets. By using 3D printing to build protective structures, future settlers could create safe environments to live and work, significantly enhancing their chances of survival in a hostile environment. The incorporation of 3D printing into space missions is not just a theoretical concept. Successful experiments have already been conducted aboard the International Space Station, demonstrating the feasibility of printing objects in microgravity. The potential of 3D printing in space is vast and still largely untapped, representing a frontier of innovation that could redefine how humanity approaches space exploration. As we continue to push the boundaries of what is possible, 3D printing stands out as a key technology that could enable us to venture further into the cosmos, building the tools and infrastructure needed to. Cosmic radiation, a form of ionizing radiation that comes from outer space, is something we often overlook, yet it plays a significant role in our lives, even if we are not aware of it. As we spend our days on Earth, we are constantly exposed to this radiation, which originates from the sun and other celestial bodies, traveling through the universe, and reaching us in varying amounts depending on several factors, including altitude and geographical location. For instance, people living at higher altitudes, such as in the Rocky Mountains, receive a higher dose of cosmic radiation compared to those at sea level, primarily because the atmosphere, which acts as a protective shield, is thinner at higher elevations. Interestingly, cosmic radiation is made up of highly energetic particles, including protons, alpha particles, and heavy ions that can penetrate the human body and, in some cases, cause damage to our cells and DNA. This raises questions about the potential health effects of long-term exposure. Studies have shown that, while the average person is exposed to a relatively low dose of cosmic radiation, astronauts who venture into space face much higher levels, which could increase their risk of developing health issues such as cancer, cataracts, and cardiovascular diseases. Research indicates that the higher the radiation dose, the greater the risk of these health problems, making it crucial for space agencies to monitor and mitigate exposure for astronauts during their missions. Moreover, cosmic radiation is not just a concern for astronauts. It also affects airline crew and frequent flyers, who are exposed to elevated levels of radiation during long flights, particularly on polar routes where the Earth's magnetic field provides less protection. The cumulative effect of this exposure is still a topic of ongoing research, as scientists strive to understand the implications of increased cosmic radiation on human health over time. Some studies suggest that, while the risks are present, the actual impact on health may be relatively small for those who fly frequently, but it remains essential to consider occupational safety and health guidelines to minimize risks. Additionally, cosmic radiation has been a topic of interest in the field of climate science, as it may influence cloud formation and, consequently, weather patterns. Some theories propose that variations in cosmic radiation could correlate with changes in Earth's climate, highlighting the interconnectedness of cosmic events and terrestrial phenomena. The medical community also studies cosmic radiation for its potential applications in cancer treatment, where certain types of radiation, including those similar to cosmic rays, can be harnessed to target and destroy cancer cells. This cross-disciplinary, the ethics of interstellar exploration, a topic that sparks both excitement and deep philosophical questions, raises important issues about our responsibilities as we consider venturing beyond our own solar system. As technology advances, the prospect of sending spacecraft to distant stars becomes more tangible, yet it brings with it a host of ethical dilemmas. One pressing concern is the potential impact on any extraterrestrial ecosystems we might encounter. If we were to discover planets with life, even microbial forms, What right do we have to interfere with their natural development? This question challenges us to think about stewardship and whether we should prioritize exploration over conservation, especially when we consider how fragile life can be, even here on Earth. Additionally, there's the matter of our own motivations for exploring the cosmos. Are we driven by a genuine desire for knowledge? Or are we simply looking for new resources to exploit, as has often been the case throughout human history? This leads to the ethical implications of colonialism, as some argue that our expansion into space could mirror the colonial adventures of the past, where the interests of the powerful overshadowed the rights and cultures of the indigenous peoples. In an interstellar context, this raises the question of what it means to be a responsible explorer, and how we can ensure that our actions do not repeat the mistakes of our ancestors. Moreover, there is the issue of the potential for contact with intelligent alien civilizations. If we were to make contact, how would we engage with them? Would we approach with humility and a willingness to learn? Or would we impose our own values and systems upon them? The ethical frameworks we develop now could guide us in these scenarios, emphasizing the importance of mutual respect and understanding, rather than domination or conflict. The potential for misunderstanding or miscommunication could lead to disastrous consequences, not just for us, but for any extraterrestrial beings we encounter. Then there's the aspect of technological development and its implications. As we develop the technologies necessary for interstellar travel, we must also consider the ethical ramifications of those technologies. For instance, artificial intelligence, which could play a crucial role in exploring distant worlds, raises questions about autonomy, control, and the rights of sentient beings that may arise from such advancements. How do we ensure that our creations do not turn against us or become uncontrollable? This introspection is vital as we navigate the complex landscape of ethics in science and technology. Lastly, the exploration of space also brings about considerations related to the well-being of future generations. As we embark on this journey, education plays a crucial role in promoting space careers, as it lays the foundation for the skills and knowledge that are essential in this rapidly evolving field. From a young age, students are introduced to the wonders of space through science classes, planetarium visits, and engaging activities that spark curiosity about the universe. As they progress through their education, subjects like mathematics, physics, and engineering become increasingly important, providing the technical skills needed for various roles in the aerospace industry. Higher education institutions, such as universities, have developed specialized programs that focus on aerospace engineering, astrophysics, and planetary science, allowing students to dive deep into the complexities of space exploration. Moreover, educational outreach programs, often conducted by space agencies and organizations, aim to inspire the next generation of scientists, engineers, and astronauts. These programs often include workshops, internships, and mentorship opportunities, helping students gain practical experience while also connecting them with professionals in the field. Events like National Space Day and International Space Week further promote awareness of space careers, encouraging students to consider how they can contribute to future explorations and advancements in technology. In addition, online courses and resources have made space education more accessible than ever, enabling individuals from diverse backgrounds to explore this exciting field. Whether through free online classes offered by prestigious universities or interactive simulations that allow students to experience space missions virtually, the resources available today are abundant, fostering a greater interest in space-related careers. Furthermore, collaborations between educational institutions and space agencies, such as NASA and ESA, create pathways for students to engage in real-world projects, offering them invaluable experience that enhances their resumes and prepares them for future employment. Programs like NASA's Artemis Challenge and the European Space Agency's Space Education Program challenge students to solve real problems faced in space exploration, encouraging innovation and critical thinking. Importantly, diversity in education is also emphasized, as the space industry benefits from a wide range of perspectives and ideas. Initiatives aimed at increasing participation from underrepresented groups in STEM fields are crucial, as they help to ensure that the workforce is not only skilled, but also reflective of society as a whole. Overall, education serves as a vital tool in cultivating interest and preparing individuals for careers in space, providing them with the knowledge, experience, and inspiration needed to push the boundaries of what is possible in our exploration of the cosmos. The journey from classroom to career in the space sector is filled with opportunities for growth, collaboration, and discovery, encouraging students to reach for the stars, quite literally. Virtual reality, or VR, is revolutionizing space training in remarkable ways, providing astronauts with immersive experiences that prepare them for the challenges of space exploration. Traditional training methods, often limited to simulations and physical exercises, are being enhanced by the incorporation of VR, allowing astronauts to engage in realistic scenarios that they would encounter in space. For instance, VR enables trainees to experience microgravity environments, which is critical for understanding how to maneuver and operate equipment in space. This technology can mimic the sensation of floating, helping astronauts to adjust their movements and reactions as if they were actually in space, rather than simply practicing on Earth. Moreover, VR offers the ability to recreate specific missions and environments, such as the surface of Mars or the interior of the International Space Station. This kind of immersive training can significantly reduce the anxiety and uncertainty that astronauts might feel when they encounter these environments for the first time. By virtually walking on the lunar surface or navigating the corridors of a spacecraft, trainees can build confidence and familiarity, which are essential for mission success. Additionally, VR allows for risk-free training scenarios. Astronauts can practice emergency protocols, such as dealing with equipment malfunctions or conducting spacewalks, without the real-world consequences of failure. This means they can make mistakes, learn from them, and refine their skills in a safe, controlled environment. The ability to repeat and practice these scenarios as many times as needed ensures that astronauts are well prepared for any situation they may face during their missions. Another significant benefit of VR in space training is the collaboration it fosters. Teams can train together in a shared virtual space, regardless of their physical locations. This is especially important for international missions, where astronauts from different countries may need to work together seamlessly. By using VR platforms, teams can simulate joint exercises, improve communication, and build camaraderie, all of which are crucial for successful cooperation in the high-pressure environment of space. Furthermore, VR technology is constantly evolving, becoming more sophisticated and accessible. As hardware improves, the simulations become more realistic, allowing for enhanced training experiences. With advancements in haptic feedback, astronauts can not only see and hear the virtual environments, but also feel them, creating a more comprehensive training experience. This level of detail can help them better understand the physical challenges they will encounter, such as the handling of tools or the operation of machinery in a zero-gravity setting. The impact of VR on space training extends beyond just the astronauts. Ground control teams and support staff can also benefit from this. Space exploration has long been a source of fascination, not just for scientists and engineers, but for all of humanity. As we look towards the stars, it's important to consider how our ventures into space impact global security, which is a topic of growing relevance in today's world. The increasing presence of satellites in orbit has revolutionized communication, navigation, and surveillance, but it has also introduced new challenges and risks. Countries are now able to monitor military movements, track natural disasters, and even gather intelligence, all thanks to this technological leap. However, this capability comes with concerns about privacy, espionage, and the militarization of space. The potential for conflict in space has become a pressing issue as nations race to develop advanced technologies. For instance, the United States, Russia, and China are investing heavily in their space programs, not only for exploration, but also for national security purposes. The concept of space as a new theater of war raises alarms among experts, as the possibility of weaponizing space could lead to an arms race beyond our planet. The idea of anti-satellite weapons, which can destroy or disable satellites, poses a significant threat to the delicate balance of global security, as these devices could be used in conflict to disrupt communications and navigation systems on Earth. Moreover, the increasing number of satellites in orbit creates a risk of collisions, which could generate space debris, further complicating the security landscape. This debris can damage operational satellites, leading to loss of capabilities that are essential for national security and everyday life. Countries are now challenged to develop regulations and guidelines to ensure the safe use of space, while mitigating the risks associated with overcrowded orbital paths. In addition to traditional military concerns, space exploration also raises questions about international cooperation and governance. Initiatives like the Outer Space Treaty, which was established in 1967, aim to promote peaceful use of outer space and prevent the placement of nuclear weapons in orbit. However, as new technologies emerge and more countries seek to explore space, there is a need to revisit and strengthen these agreements to reflect the current landscape. Furthermore, the role of private companies in space exploration adds another layer of complexity to global security. With companies like SpaceX and Blue Origin leading the charge in launching satellites and developing space tourism, the boundaries between governmental and commercial interests become blurred. This trend necessitates new frameworks for accountability and regulation, ensuring that private entities contribute positively to the security landscape rather than exacerbate tensions. While the challenges are significant, space exploration also offers opportunities for the future of spacecraft design is an exciting realm filled with innovation, creativity, and advancements in technology. As engineers and scientists explore new materials, concepts, and systems to enhance our ability to explore the cosmos, one of the key trends shaping future spacecraft design is the use of lightweight materials, such as advanced composites and even metals that are both strong and lightweight, allowing for more efficient structures. This not only reduces the overall weight of the spacecraft, but also improves fuel efficiency, meaning that spacecraft can carry more payload or travel further on the same amount of fuel. In addition, 3D printing technology is making waves in spacecraft design, enabling manufacturers to produce complex parts on demand, which can significantly reduce costs and lead times. This technology opens doors for creating intricate designs that were previously impossible or too expensive to manufacture. Another fascinating aspect is the integration of artificial intelligence and machine learning into spacecraft systems. These technologies can help optimize flight paths, manage onboard systems more efficiently, and even assist in autonomous decision-making during missions, which is crucial for deep space exploration, where communication delays with Earth can be substantial. As missions become more ambitious, with plans for manned trips to Mars and beyond, the need for reliable, self-sufficient spacecraft is paramount. In this context, the design of life support systems is evolving as well, with a focus on sustainability and recycling. Future spacecraft may incorporate bioregenerative systems that recycle air and water, and even grow food in space, ensuring that astronauts can sustain themselves on long-duration missions. Moreover, the concept of modular spacecraft design is gaining traction, allowing parts of the spacecraft to be built separately and then assembled in orbit or on other celestial bodies. This approach not only simplifies construction, but also facilitates upgrades and repairs, making spacecraft more adaptable to various missions and conditions. Furthermore, as we look toward the exploration of other planets and moons, the idea of utilizing in-situ resource utilization, or ISRU, is becoming increasingly important. This involves designing spacecraft that can utilize local resources, like water ice on the Moon or Mars, to produce fuel or oxygen, reducing the need to transport everything from Earth. As we gaze into the future, we also must consider the role of sustainability in spacecraft design. With growing concerns about space debris, engineers are now tasked with creating designs that minimize waste and enhance the longevity of spacecraft. Innovations, such as deorbiting systems that ensure defunct satellites and spacecraft can safely re-enter the atmosphere, are being developed to tackle the issue of space junk. Citizen science has become an increasingly vital component in the field of space research, enabling everyday people to contribute to significant scientific discoveries and expand our understanding of the universe. This collaborative approach allows enthusiasts, students, and the general public to engage in various projects, often through online platforms where they can analyze data, identify celestial objects, and even assist in monitoring space phenomena. One well-known example is the Galaxy Zoo project, which invites volunteers to classify millions of galaxies based on their shapes, contributing to our knowledge of galaxy formation and evolution. By harnessing the power of the crowd, researchers can process vast amounts of data more quickly than if they relied solely on trained scientists, making it possible to tackle complex questions about the cosmos. Moreover, citizen science has been instrumental in the search for exoplanets, with platforms like Planet Hunters allowing volunteers to sift through data from telescopes, looking for the subtle dips in light that indicate the presence of a planet passing in front of its star. This not only accelerates the pace of discovery, but also fosters a sense of community among participants who share their findings and learn from one another, creating a collaborative learning environment. In addition to exoplanets, citizen scientists have contributed to projects aimed at tracking near-Earth objects, helping to identify potentially hazardous asteroids by analyzing images and data collected from various telescopes. Furthermore, citizen science initiatives often help raise awareness about space science and its significance, encouraging more people to become interested in STEM fields. This grassroots involvement can inspire future generations of scientists, engineers, and explorers, as participants often gain first-hand experience in scientific methods and critical thinking. Engaging with space research also provides an opportunity for individuals to connect with the larger scientific community, attending workshops, lectures, and even working alongside professional astronomers during collaborative events. Another fascinating aspect of citizen science in space research is the use of mobile applications, which allow people to engage with scientific research from anywhere, at any time. For example, apps like Starwalk or Sky Safari enable users to explore the night sky, identify stars and constellations, and report their observations, making astronomy more accessible and interactive. This democratization of knowledge empowers individuals to become active participants in the scientific process, rather than passive observers, creating a more informed and engaged public. In addition, citizen scientists often contribute to important ecological and environmental studies that intersect with space research, such as monitoring the impact of climate change on celestial observations. By understanding how light pollution affects our ability to observe the night sky, the discovery of extraterrestrial intelligence, if it were to occur, would undoubtedly have a profound cultural impact on humanity, reshaping our views on existence, society, and our place in the universe, as well as challenging our philosophical beliefs and scientific paradigms. Imagine, for a moment, the moment when people around the world receive credible evidence of intelligent life beyond Earth. It would likely spark an unprecedented wave of curiosity and excitement, prompting us to reconsider our definitions of life and intelligence. Many cultures, religions, and beliefs might be affected, as ancient texts and myths could be reinterpreted in the light of new knowledge, leading to fascinating discussions about the role of humanity in a broader cosmic context. Artists, writers, and filmmakers would likely find themselves inspired, producing a myriad of works that reflect on this new reality, exploring themes of connection, communication, and the potential for interstellar diplomacy. The emergence of extraterrestrial beings might even lead to a renaissance in art and literature, as creators channel their imaginations into exploring what these encounters might mean for humanity. Social media, news outlets, and academic circles would buzz with debates and discussions, as people from different backgrounds share their thoughts and feelings about the implications of such a discovery. Moreover, the scientific community would be invigorated, as researchers from diverse fields, such as biology, astronomy, and anthropology, would collaborate to study the implications of extraterrestrial life. New branches of science could emerge, focusing on astrobiology and xenolinguistics, the study of potential alien languages, which would challenge our understanding of communication and consciousness. The educational sector might also see significant changes, with schools and universities incorporating new curricula that reflect our interstellar reality, fostering a generation that is more aware of the universe and our place within it. The political landscape could shift dramatically, as nations might unite in the pursuit of understanding and interacting with extraterrestrial beings. Or, conversely, there could be competition over resources related to this new frontier. International treaties could be established to govern interactions with alien civilizations, reflecting humanity's desire for peace and cooperation. Or, on the other hand, fears of conflict and misunderstanding could lead to tensions. This development would also pose ethical questions about how we treat these new beings, should they be discovered, and what rights they might have. Religious groups might experience a range of responses. Some might embrace the idea of extraterrestrial intelligence, seeing it as an extension of the divine creation, while others might struggle to reconcile their beliefs with the concept of space colonies, while often regarded as the stuff of science fiction, is increasingly being examined for its economic viability, and one of the most compelling aspects of this discussion revolves around the potential benefits and challenges that such colonies could present. First, let's consider the resources available in space, particularly on celestial bodies like the Moon and Mars. These locations are thought to harbor a variety of materials, including water ice, which can be converted into oxygen and hydrogen, essential for sustaining human life, and possibly even for creating rocket fuel for further space exploration. This means that space colonies could, in theory, become self-sustaining, reducing the need for constant supply shipments from Earth, which are costly and time-consuming. Additionally, the idea of mining asteroids is gaining traction, as these celestial bodies are believed to contain valuable metals and minerals, such as gold, platinum, and rare earth elements, which are vital for technology on Earth. The potential for profit from asteroid mining could drive the economic viability of establishing colonies in space. Companies like Planetary Resources and Deep Space Industries are already exploring these possibilities, indicating a growing interest in the commercial aspects of space exploration. Furthermore, advancements in technology are reducing the costs associated with launching payloads into space, which could make the establishment of colonies more feasible. However, there are significant challenges to consider as well. The initial investment required for creating a sustainable colony is astronomical, involving the construction of habitats, life support systems, and infrastructure to support human activity. Governments, private companies, and international collaborations would need to collaborate to share the financial burden and reduce individual risk. The question of governance and regulation also arises, as the Outer Space Treaty of 1967 stipulates that space shall be free for exploration and use by all. But it also leaves many legal questions unanswered. If a colony were to be established, who would own it? How would resources be allocated? These are critical issues that need to be addressed to ensure that space colonies can operate effectively and fairly. Moreover, the psychological and physiological impacts of living in a space colony cannot be overlooked. Studies show that extended periods in microgravity can lead to health issues, including muscle atrophy and bone density loss, which means that any colony would need to innovate ways to keep inhabitants healthy and active. The isolation and confinement of living in a space colony could also affect mental health, necessitating robust support systems for those living far from Earth. In addition to practical considerations, the potential for tourism in space is spacecraft propulsion systems are on the brink of a revolutionary transformation, driven by the need for more efficient, faster, and versatile means of exploring the cosmos. Traditionally, chemical propulsion has dominated space travel, relying on the combustion of fuel and oxidizers to produce thrust. However, as we look to the future, several promising technologies are emerging, each with the potential to redefine how we travel beyond our planet. One of the most exciting developments is ion propulsion, which uses electric fields to accelerate ions, generating thrust with far greater efficiency than conventional rocket engines. This technology has already been successfully tested in missions like NASA's Dawn spacecraft, which traveled to the asteroid belt, demonstrating the ability to operate for extended periods, allowing for longer missions and deeper space exploration. Another innovative approach is solar sail technology, which harnesses the pressure of sunlight for propulsion. By using large, reflective sails, these spacecraft can gradually accelerate using the continuous push of photons from the sun. The Planetary Society's Light Sail mission successfully demonstrated this concept in 2020, showcasing the potential for long-duration space travel without the need for fuel. As we look further, fusion propulsion is also being explored, which could offer unprecedented speeds by harnessing the same process that powers the sun. With fusion, the idea is to create a controlled reaction that would produce thrust, potentially allowing us to reach other star systems in a human lifetime, a concept that once seemed like science fiction. Moreover, researchers are investigating the use of plasma propulsion systems, which can produce thrust by heating and expelling a plasma, offering high efficiency and the ability to operate continuously for long periods. This technology could be crucial for missions to Mars and beyond, as it would enable spacecraft to travel faster and reduce travel times significantly. Additionally, advancements in electric propulsion systems, such as Hall-effect thrusters, are gaining traction, providing reliable solutions for maneuvering satellites in orbit and potentially interplanetary travel. As we explore these cutting-edge propulsion systems, the integration of artificial intelligence and advanced materials could further enhance performance and reliability. Smart systems could optimize flight paths in real time, adapting to changing conditions in space, while lightweight, durable materials could withstand the harsh environments of deep space. With ongoing research and investment, the future of spacecraft propulsion systems holds immense promise, paving the way for a new era of exploration that could take humanity further than ever before, opening up the universe in ways we can only begin to imagine. Space communication, a vital aspect of modern space exploration, faces several significant challenges, which stem from the unique environment of space, the vast distances involved, and the technology currently available. One of the primary challenges is the enormous distance that signals must travel, as radio waves, which are used for communication, move at the speed of light, approximately 792 kilometers per second. However, even at this incredible speed, there can be considerable delays. For instance, when communicating with Mars, signals can take anywhere from 3 to 20 minutes to travel one way, depending on the planet's positions in their respective orbits. This delay poses a challenge for real-time communication, making it difficult for astronauts or rovers to receive immediate feedback or instructions from mission control on Earth. Moreover, the vast distances can lead to signal degradation. As signals travel, they can lose strength, and this is especially true when they pass through the Earth's atmosphere or when they encounter obstacles like interplanetary dust. This degradation can result in a loss of data or the need for more powerful transmitters, which adds complexity and cost to missions. Additionally, the frequency of communication can be influenced by the solar activity, such as solar flares, which can disrupt signals and create interference, further complicating the communication process. Another significant challenge is the need for advanced technology to ensure effective communication. Spacecraft and satellites must be equipped with sophisticated communication systems, including antennas that can adjust to different frequencies and technologies that can encode and decode data efficiently. The development of these technologies requires continuous research and investment. As the demands of deep space missions increase, new technologies, such as laser communication, offer the potential for higher data rates and more reliable connections, but they also require new infrastructure and training. Furthermore, the human factor cannot be overlooked, as astronauts must be trained to handle communication equipment, as well as to deal with the emotional and psychological challenges of being isolated from Earth. Communication is not just about sending and receiving data, it is also about maintaining morale among astronauts, who may experience feelings of loneliness or disconnect due to the time delays and the physical distance from their families and loved ones. In addition, there are significant logistical challenges in setting up communication networks for missions beyond Earth, such as establishing relay satellites around the Moon or Mars to enhance communication capabilities. This requires careful planning and collaboration among international space agencies, as well as the need for sustainable practices to ensure that these networks can operate effectively over long periods. Finally, as we look toward the future of space exploration, the role of women in space missions is becoming increasingly significant, reflecting broader changes in society and science. Historically, women have played vital roles in space exploration, though often behind the scenes. However, as we move into the next era of space discovery, their contributions are expected to become more prominent, with NASA and other space agencies actively promoting gender equality in their missions. For instance, the Artemis program, which aims to return humans to the Moon by the mid-2020s, has made headlines by including a woman among the first set of astronauts who will set foot on the lunar surface. This initiative is not just about symbolic representation. It signifies a shift in the space industry, emphasizing the importance of diverse perspectives and experiences in overcoming challenges and fostering innovation. Women like Dr. Jeanette Epps, who is slated to become the first Black woman to live and work on the International Space Station, exemplify the growing presence of women in leadership roles within space agencies. This representation is crucial, as it encourages young girls and women to pursue careers in STEM fields, which have historically been male-dominated. Programs aimed at mentoring and inspiring women to enter these fields are gaining traction, and more women are pursuing advanced degrees in aerospace engineering, astrophysics, and planetary science, thus enriching the talent pool available for future missions. Moreover, as we consider long-duration space missions, such as those to Mars, understanding the unique physiological and psychological impacts on women becomes essential. Research indicates that women may experience different effects in microgravity compared to men, and understanding these differences is vital for mission success. This means that future space missions will likely include more comprehensive studies on how women adapt to space environments, ensuring that all astronauts are well prepared for the rigors of space travel. The collaboration between international space agencies, such as the European Space Agency and NASA, also emphasizes the role of women, as these organizations strive to create inclusive teams that better represent the global population. By fostering diverse teams, agencies can leverage a wider array of ideas and solutions, enhancing problem-solving capabilities when facing the unknowns of space. In addition, private companies entering the space race are also recognizing the importance of women in their ranks. With companies like SpaceX and Blue Origin pushing the boundaries of space technology, the inclusion of women in engineering, piloting, and mission design roles is becoming more common, further breaking down stereotypes and challenging the status quo. The increasing visibility of women in these positions. When we think about space exploration, we often imagine the exciting launch of rockets, the thrilling missions to distant planets, and the possibility of discovering new worlds. But behind this fascinating adventure lies a significant environmental concern that cannot be overlooked. Space launches, while essential for scientific advancement, have an impact on our planet's environment. And understanding these effects is crucial for the future of both space travel and Earth's health. One of the primary concerns regarding space launches is the emissions produced by rockets. Traditional rocket propellants, many of which are based on hydrocarbons, release greenhouse gases, such as carbon dioxide and water vapor, into the atmosphere. These emissions contribute to climate change, and while the number of launches is currently much lower than other major sources of emissions, such as aviation or automobiles, the increase in commercial spaceflight could amplify this problem in the future. Furthermore, certain rocket fuels, like those containing chlorine, can produce ozone-depleting substances when released into the upper atmosphere, which is particularly concerning given the already fragile state of the ozone layer. Another environmental issue tied to rocket launches is the potential for air pollution. During launch, rockets emit not only gases, but also particulate matter, which can affect air quality in the vicinity of launch sites. This can pose health risks for people living near these areas, especially if launches are conducted frequently. The noise generated during a rocket launch is also significant, creating disturbances that can impact local wildlife, particularly birds and other animals that rely on sound for communication and navigation. Moreover, the physical impact of rocket launches on local ecosystems is an area of growing concern. Launch sites are often constructed in remote locations, which can disrupt natural habitats and wildlife corridors. The preparation for launches involves significant land clearing, construction of infrastructure, and increased human activity, all of which can lead to habitat destruction, fragmentation, and increased human-wildlife conflicts. For instance, sensitive coastal areas, which are often chosen for their open space and access to water, can be particularly vulnerable to such disturbances. Space debris is another pressing issue that has environmental implications. As more rockets are launched, the number of satellites and other objects in Earth's orbit increases, leading to the potential for collisions that could generate even more debris. This space junk poses risks not only to operational satellites, but also to future missions, and the long-term consequences of a cluttered orbit could hinder humanity's ability to utilize space safely and sustainably. Additionally, the extraction of resources for rocket manufacturing and fuel production can have significant environmental. Quantum computing, a fascinating and complex field, has the potential to revolutionize many areas of technology, including space exploration. At its core, quantum computing leverages the principles of quantum mechanics, allowing for computations that would be impossible or take an impractical amount of time for classical computers. This capability is particularly important in the context of space exploration, where the challenges are immense and the data is vast. For instance, space missions generate enormous amounts of data, from analyzing the surfaces of distant planets to monitoring cosmic phenomena. Quantum computers could process this data far more efficiently than traditional computers, enabling scientists to make discoveries that were previously out of reach. One exciting application of quantum computing in space exploration is in the realm of simulation. Space missions often rely on detailed simulations to predict the behavior of spacecraft, the effects of various gravitational forces, and the interactions between different celestial bodies. Quantum computers can simulate these complex systems with greater accuracy and speed, which could lead to more successful missions. For example, simulating the climate of Mars or the potential for life on exoplanets could become much more feasible with quantum technology, providing insights that help guide future exploration efforts. Moreover, quantum computing could enhance our ability to solve optimization problems, which are common in space missions. For instance, determining the most efficient path for a spacecraft, minimizing fuel consumption while maximizing scientific output, is a complex problem that could benefit from quantum algorithms. These algorithms can explore numerous possibilities simultaneously, leading to faster and more effective solutions compared to classical approaches. As space agencies look to send missions further into the solar system and beyond, the need for optimized mission planning becomes increasingly critical, making quantum computing a valuable tool. Additionally, quantum communication, another branch of quantum technology, holds promise for improving the way we communicate with spacecraft and satellites. The vast distances involved in space travel can lead to delays and potential loss of data. Quantum communication systems could provide more secure and reliable connections between Earth and space, enabling real-time data transmission and reducing the risk of information loss. This could be especially beneficial for missions to distant planets or for sending data from orbiting telescopes studying the universe. Some researchers are already exploring the potential of quantum computing for analyzing astronomical data, such as that collected from telescopes observing distant galaxies. The patterns and signals captured by these telescopes can be incredibly complex, and traditional methods of data analysis may fall short. Quantum algorithms could help identify patterns and anomalies more effectively, unlocking new insights into the formation of the universe and the behavior of. Throughout the history of space exploration, numerous missions have provided valuable lessons that continue to shape our understanding of space travel, technology, and even international cooperation. One of the most significant missions, the Apollo program, which landed humans on the moon between 1969 and 1972, taught us not just about the complexities of space travel, but also about the importance of meticulous planning, teamwork, and adaptability. The Apollo 13 mission, in particular, stands out as a remarkable example of problem-solving under pressure. When an oxygen tank exploded, the crew and mission control had to work together, using limited resources to devise a plan to bring the astronauts home safely, showcasing the power of innovation and collaboration in the face of adversity. In addition, the Space Shuttle program, which operated from 1981 to 2011, provided critical insights into reusable spacecraft design, safety protocols, and the importance of continuous improvement. The tragic losses of the Challenger and Columbia missions highlighted the necessity of a robust safety culture, as well as the need for transparent communication in high-stakes environments. These events led to significant reforms in NASA's safety practices, emphasizing the need for thorough investigation and change following accidents, a lesson that can apply to many fields beyond aerospace. The International Space Station, a collaborative effort involving multiple countries, has shown us that international partnerships can yield scientific advancements that benefit all of humanity. Over its 2 decades of operation, the ISS has fostered cooperation between nations that might otherwise be in conflict, proving that shared goals, such as scientific research and exploration, can unite people across political boundaries. The diverse crew on the ISS has conducted experiments that have expanded our understanding of biology, physics, and Earth science, leading to innovations that impact life on our planet. Furthermore, robotic missions, like the Mars rovers, have taught us about the importance of remote exploration. Rovers like Curiosity and Perseverance have not only provided critical data about the Martian environment, but have also pushed the boundaries of technology, demonstrating how we can explore and gather information from places that are too dangerous or far away for humans to visit. These missions stress the significance of adaptability in technology, as they often require quick fixes and software updates to respond to unforeseen challenges on alien terrains. Moreover, the Hubble Space Telescope has revolutionized our understanding of the universe, showing how long-term investments in technology can yield extraordinary results. Hubble's ability to capture stunning images and gather data over decades has provided insights into the rate of expansion. Space agencies play a crucial role in addressing global challenges, not only through their primary missions of exploration and scientific discovery, but also by applying their technologies and expertise to solve pressing problems on Earth. For instance, agencies like NASA, ESA, and ISRO have developed satellite systems that monitor climate change, track natural disasters, and provide critical data for agricultural planning, thus helping communities adapt to changing environmental conditions. These satellites collect vast amounts of information about weather patterns, greenhouse gas emissions, and land use changes, which are essential for understanding and mitigating climate-related risks. Moreover, space agencies are increasingly collaborating with international organizations, governments, and private sectors to strengthen disaster response capabilities. For example, during natural disasters such as hurricanes or earthquakes, satellite imagery can provide real-time information about affected areas, enabling quicker and more effective humanitarian responses. The data helps in assessing damage, coordinating relief efforts, and planning recovery strategies, ultimately saving lives and resources. In addition to disaster management, space agencies are at the forefront of advancing technology that addresses food security. By using remote sensing technology, they help monitor crop health, predict yields, and manage water resources. This information is vital for farmers, especially in regions facing extreme climate variability, as it allows them to make informed decisions about planting and harvesting, thereby optimizing food production and reducing waste. Furthermore, space agencies contribute to global health initiatives by providing data essential for tracking diseases and monitoring public health trends. For instance, satellite data has been used to track the spread of diseases like malaria and dengue fever, allowing health organizations to implement targeted interventions. This intersection of space technology and public health demonstrates how the capabilities developed for space exploration can also benefit society on Earth. The role of space agencies extends into the realm of sustainable development as well. They are involved in initiatives aimed at promoting clean energy, improving urban planning, and fostering environmental conservation. For example, satellite data can support renewable energy projects by identifying optimal locations for solar and wind farms, thus facilitating the transition to a more sustainable energy future. Lastly, the growing field of space debris management highlights the importance of space agencies in safeguarding the future of space exploration itself. As the number of satellites and space missions increases, the risk of collisions and space debris becomes a significant concern. Space agencies are actively working on strategies to track and mitigate space debris, ensuring that the benefits of space exploration can be enjoyed by future generations without compromising the safety of orbital operations. Through these multifaceted approaches, space agencies not only push the boundaries of human as we delve into the future of human spaceflight beyond low Earth orbit. It's essential to understand the ambitious visions that space agencies and private companies are pursuing. One of the most exciting developments is NASA's Artemis program, which aims to return humans to the moon by the mid-2020s, establishing a sustainable presence that could pave the way for future missions to Mars. This initiative includes the construction of the Lunar Gateway, a small space station that will orbit the moon, serving as a hub for lunar exploration and a staging point for deeper space missions, thereby enhancing our capabilities for long-duration space travel. Meanwhile, SpaceX is making remarkable strides with its Starship, designed to carry crew and cargo to various destinations, including the Moon and eventually Mars. Starship's fully reusable design could significantly reduce the cost of space travel, making it more accessible, while its capacity for carrying large crews and equipment is crucial for ambitious missions. The idea of establishing a human settlement on Mars is gaining traction, with plans to develop technologies for life support, habitat construction, and in-situ resource utilization, allowing astronauts to use Martian resources for fuel and other necessities. In parallel, there are exciting prospects for international collaboration in space exploration. The International Space Station has already demonstrated the benefits of working together, and as we look beyond low Earth orbit, partnerships among nations could lead to shared missions to the Moon, Mars, and even asteroids. This collaborative spirit not only fosters goodwill on Earth, but also pools resources and expertise, making ambitious projects more feasible. Moreover, advancements in technology are set to enhance our understanding of how humans can live and work in space for extended periods. Research on the effects of microgravity on the human body continues to inform us about health risks, such as muscle atrophy and radiation exposure, paving the way for countermeasures that will allow astronauts to thrive during long missions. These insights are essential for planning long-duration stays on Mars or for potential missions to the outer planets. As we consider the future of space travel, the concept of space tourism is also emerging, with companies like Blue Origin and Virgin Galactic working to make suborbital flights a reality for civilians. While this may seem like a luxury for the wealthy, the technology developed for space tourism could eventually contribute to broader access to space and inspire the next generation of explorers. In addition, the potential for mining asteroids is becoming a topic of interest, as these celestial bodies may hold valuable resources such as metals and water. The